Okay. Hi everyone. Hi. Hi. Okay. So where were we? We were saying that we talked about dimensionality of derivative in the previous session. Hi. And then now let's talk about gradient and Hessian. We have and Jacobian. So in simple words, so gradient, Jacobian, and first order derivative, they are the same thing. Okay, but usually when we are there, the first order derivative becomes a vector, we call it gradient usually. Okay, also gradients might be a matrix, that's fine. But usually we are taking derivative of a scalar function whose output is a scalar with respect to some vector, right? And then, therefore, derivative of a scalar with respect to a vector becomes a vector, and we call that gradient, and we can denote it either in this way or in this way. It's a vector. However, when we have the derivative of a vector with respect to another vector, in that case, the first order derivative becomes a matrix. Usually, sometimes we call the matrix first order derivative Jacobian. So what do I mean? So if f is Rd to Rp, for example, then derivative of f with respect to x becomes Rd by p or p by d. In this case, this becomes a Jacobian. What do I mean by this? It will be, so because f itself, so this is f1 until fp transpose. What is this? This is x1 until xd transpose. Do you agree? Right. Therefore, you can write it in this way. Derivative of f1 with respect to x1 until derivative of f1 with respect to xd. Also here, derivative of fp with respect to x1 until derivative of fp with respect to xd. And all other elements. So the elements of this derivative becomes derivatives of each elements of f with respect to each element of x, right? And as you see, these are partial derivatives. So in this case, we usually also call this Jacobian matrix. And as you see, both Jacobian and gradient are the first order derivatives. And by the way, you might be wondering, when we say derivative of a vector with respect to another vector, such as in this case, should it be a d by p matrix or a p by d matrix? Which one? If you ask me this question, meaning that you're picky on these things, I'm saying that doesn't matter. Choose one convention and stick to that convention until the end. What do I mean by until the end? Because usually you have matrix multiplications. If you choose d by p, then the other derivatives that you have need to be taken in this way for the matrix dimensionalities of matrices to match in matrix multiplication. Otherwise, you will have nonsense matrix multiplications. Do you agree? You understand what I'm saying there? Because in matrix multiplications, the dimensionalities of matrices should match with each other. So stick to one convention until the end. Otherwise, you will have nonsense matrix multiplications. And what is Hessian? Hessian just is a second order derivative. As we usually, the function usually is a scalar and the variable is a vector, then the second order derivative becomes a matrix. Why? You can see second order derivative as the first order derivative of the first order derivative, right? For once, let's take the first order derivative. What will it be? It will be a vector. Then take the derivative of that d-dimensional vector with respect to x, which is also d-dimensional. Then you will have a matrix D by D. Hence, Hessian is a square matrix. It's not a rectangular matrix. It's a square matrix. Also, it's symmetric. And if the function is convex, the Hessian matrix is positive semi-definite. Why? Because if you remember, for scalar functions, in this case, when the function is facing up, the second order derivative is positive. When it is facing down, the second order derivative is negative, right? We learned that in high school. So that was for scalar functions. But in multi-dimensional functions, when the function's output is not necessarily a scalar, then we don't say that the second order derivative must be positive or negative, because the second order derivative is a matrix, and we don't say whether a matrix is positive or negative. We say whether a matrix is positive semi-definite or not. So if it is positive semi-definite, it is facing up. If it is negative semi-definite in a region, in a neighborhood, in that region is facing down. And what do I mean by positive semi-definite? I mean its eigenvalues are all non-negative. And what do I mean by negative semi-definite? All its eigenvalues are non-positive. Yeah. Question? No? Okay. So chain rule, I think you know chain rule, right? But chain rule is simple. It says that assume I said I want to take derivative of Benjamin with respect to desk rather than that. So what does this mean? It means derivative of Benjamin with respect to desk means change the desk and see how much Benjamin changes, right? How much it modifies or impacts Benjamin. So rather than saying that derivative of Benjamin with respect to desk, you can say derivative of Benjamin with respect to laptop times derivative of laptop with respect to desk. In this case, it means that move the desk, see how much it modifies the laptop, and then that change of laptop, how much does that change Benjamin, right? So in this case, so an example is this: derivative of f of x with respect to x. You can see that derivative of f of x with respect to g of x times derivative of g of x with respect to x, where f of x is the square root of g of x, right? In this case, then derivative of f of x with respect to g of x is just, if we use the formula for derivative of square root, and also this derivative of this term is this with respect to x. So you will have this. This is a chain rule, right? And just for interested students, I'm not going into this detail. Just when we have derivatives of a matrix with respect to a matrix, or a vector with respect to a matrix, we will deal with tensors, right? Working with tensors in linear algebra and matrix multiplication is hard, right? So what should we do in these cases? When I have derivative of vector with respect to a matrix, what happens? You know that? Can you give me suggestions for handling such cases? In this case, I can simply vectorize or reshape them, right? When it becomes, for example, a rank 3 tensor, so it becomes like a cube, right? I can reshape the whole cube to become one vector. Do my matrix multiplications and vector multiplications. At the end, I reshape it back to the desired dimensionality. And how do I guess the dimensionality? By the analysis that we had. You can guess what dimensionality you should have, right? Okay.
Why do we need reshape here?
So, as I said, assume when I have, for example, A times matrix B times vector X, something like that, right? When you have, so this is matrix, right? With some dimensionality. This is matrix. This is vector. How can I write a rank 3 tensor in matrix multiplication? It's too hard, at least for me. Okay, so we can say rather than that, when we have rank 3 tensor, we can vectorize it, that tensor. This becomes a vector now, like x. Then you can simply multiply the terms to each other. At the end, you vectorize it back or devectorize it, vectorize inverse, and it becomes a tensor again. However, in vectorizing, you don't care about the dimensionality. Do you agree? In vectorization, you don't care. Whatever you have, vectorize it. In devectorization, you need to have the shape. For example, you have a vector, you want to devectorize it to become a matrix with A rows and B columns. So for devectorization, you need to know the dimensionalities. But for vectorization, you don't care. Okay. For some examples of this, by the way, this is out of the scope of the course, but for some examples, you can feel free to see some of my papers. I have used these techniques. Also, I think I have some example in the preliminaries slides of the optimization course. Okay. Okay, so briefly mentioning this, so we have this optimization problem. This is a general case where we are minimizing some f of x with respect to x subject to M1 inequality constraints and M2 equality constraints. Why do I have less than or equal to for inequality constraints? What happens to greater than or equal to? If I have that, I multiply the size by -1. So I can simply convert all of the greater than or equal to less than or equal to. Why do I have 0 always in the right-hand side? Because whatever I have, I bring it to the left-hand side. The right-hand side will have 0, right? So this is a general form of optimization. And Lagrangian says that, okay, you want to minimize this cost function, right? You also want to satisfy these equations. Simply, you can say, let's penalize these constraints as regularization terms added to the actual cost function with some weights. Do you see? These weights here in optimization, they are called either Lagrange multipliers or dual variables. Naming is not important. You can call it disk, whatever you want, right? The math behind that is important. And then you can also write it in vector form or matrix form. You understand why this becomes this, right? You understand it? This is exactly if you consider y and lambda as the vectors of their elements, this is just their inner product, right? Also here, this is the inner product of them. Then this, rather than saying minimization of this f of x subject to these constraints, the method of Lagrange multiplier says just minimize the Lagrangian. Minimize this. However, this time, in addition to the optimization variable x, which was the primal optimization variable, which is x, we should optimize with respect to the weights as well, which are the Lagrange multipliers, lambda i's and nu i's. Then what happens? This is an unconstrained optimization problem. How should we solve it? What? Derivatives, high school optimization. Take derivatives, set it to 0 with respect to each of the optimization variables, which are x, lambda i's, and nu i's. Set them to 0. This is the method of Lagrange multipliers. Okay. This is actually the backbone of most of the optimization algorithms. Okay, unconstrained optimization. Now, so that was for constraint optimization. Unconstrained, you have this. There is no constraint. So again, you take derivative, set it to 0. However, if you can find the closed form solution, done. If not, you solve it iteratively or numerically. All of the numerical methods, you can see it as this. Next thing is the previous thing plus some step, right? Now, different algorithms have different steps. How to define this step? Okay, for example, gradient method says that the step is this minus eta times the gradient, and Newton's method says the step is minus eta times the inverse of Hessian times the gradient, right? Okay. Also, for constraint optimization, we can use interior point method or proximal methods. What is interior point method? Out of the scope of this course, but just for you to know, although in one of the lectures, we will see semi-definite programming. We will not solve that, but we will say that we will end up with a semi-definite programming problem, and we'll say that can be solved using any optimization toolbox, and most of the optimization toolboxes nowadays use the interior point method. What is that? Nothing complicated. It's just generalization of Newton's method for constraint optimization. So because Newton's method is for unconstrained optimization. And interior point method simply does that. And its idea is very interesting. Just for you to know, it embeds the inequality constraint as a regularization term, similar to what we have here. Okay. However, rather than this is soft penalty, right? This what does it do? It minimizes yix, right? Do you agree? This is soft penalty. It doesn't take hard on it. What is hard penalty? I can say if yix is not less than or equal to 0, make it infinite. Minimization of infinite kills the optimization problem. Right? This is the general idea behind interior point method, although not covered in this course, but I want you to know what it is about. It's very simple. The idea is simple. It says that I have some inequality constraint. Let's add an indicator function to the cost, saying that this indicator function is 0 if this inequality constraint is satisfied. Otherwise, it becomes infinite to kill the optimization problem. Because infinity is the killer of minimization. Minus infinity is the killer of maximization. So that's the idea. Also, that's why they also call it barrier methods, because they look like barrier. They suddenly become infinite, right? What is proximal methods? It's just a special case of proximal operator is projection. Its idea is simple. It says that, so one good example is projected gradient method. You know gradient descent, right? I move one step at a time like this. This is gradient descent. Projected gradient method says do one step of, for example, this gradient descent. Then your updated solution might be out of the feasibility set. It might not satisfy the constraints. Project it back to the feasibility set to satisfy these. Then do another step of gradient descent. Then project it back. Then do. So it will be like this. For example, this is the feasibility set, and you are moving. You come here, but gradient descent, oh, it's not satisfied. So you project it here. Maybe gradient descent says, okay, you should go here. Oh, it's not satisfied. You project it back. Gradient descent next time says here, it already satisfies the feasibility set, so it stays where it was, right? And it goes until it reaches the minimum inside the feasibility set. Okay, so these are the techniques for optimization in a nutshell. Okay, now Rayleigh-Ritz quotient. Rayleigh-Ritz quotient. By the way, interrupt me whenever here. What? Turn off this one. Yeah. The reason that I leave these on for you not to sleep is because, yeah, is it good? Yeah, because it's not. The class time is night, and I don't want anyone to sleep. That's the reason I leave the lights on usually, but that's fine. Okay, so Rayleigh-Ritz quotient. This is crucial for machine learning, statistical machine learning. In deep learning, we don't have this, but in statistical machine learning, many of the algorithms deal with Rayleigh-Ritz quotient. First off, what is quotient in mathematics? So, what? You were saying? Divide? Tell me, that's if it's wrong, that's fine. What is it? Divide some, exactly, that's correct. Thank you. So we have two meanings at least for quotient. The first meaning is what you said. So it's just division. When you have a fraction, you also call it quotient, okay? And another thing is in differential geometry, it's a bit harder, and those are quotient spaces. So let's not go into that. That's a bit complicated. It's related to manifolds and Riemannian manifolds and those things. Okay, so here we are dealing with the simple meaning of quotient, just fraction. Okay, and why is it Rayleigh-Ritz? Because there are two proposers of a specific kind of quotient that we are going to talk about. Okay, Rayleigh and Ritz. So this is Rayleigh-Ritz quotient, also called Rayleigh quotient. It's this. So I define R of A and X. A is a matrix, X is a vector. The Rayleigh-Ritz quotient is a scalar, and it does that. So X transpose AX over X transpose X. You get it? As you see, the numerator is a scalar. Why? X is d by 1, A is d by d, X transpose is 1 by d. 1 by d times d by d times d by 1 becomes 1 by 1. Right? Numerator is a scalar. Likewise, denominator is a scalar because it is 1 by d times d by 1. Right? Okay, now A is a symmetric matrix. I think you expect that. Why? Usually, when we have a quadratic function, do you remember? We can either have X transpose X, or in general, we can have X transpose AX. And when A is positive semi-definite, it's a bowl facing up. When A is negative semi-definite, it's a bowl facing down. Right? If it is a scalar, if X is a scalar and A is a scalar in high school, it reduces to what we had in high school. So it becomes X squared if A is positive, or it becomes minus X squared if A is negative. Right? Okay. So as you see, everything goes back to high school. It simplifies to high school. So here, and X is non-zero vector. Why? Because we don't want to have division by 0. Right? Okay. And A is symmetric, as I said. X is non-zero. One of the properties of the Rayleigh-Ritz quotient is what? Is this. So no matter what scalar you multiply the X by, you will get the same thing. So multiplication of X by a scalar doesn't have any impact. Let's see, the proof is here. C is a scalar, right? So let's put Cx in the Rayleigh-Ritz quotient. So we'll have Cx transpose A Cx over 6 transpose 6, right? So when we have the transpose of a matrix multiplication, we see it a lot. The transpose, so let's see. So I have assume XY transpose. What does this do? The order is reversed. So it becomes Y transpose X transpose. Also, what about summation? It is applied to each element. X transpose Y. So these two, we use them a lot. Okay. So here, therefore, the order changes, but it doesn't have any impact on C. C is a scalar. So it becomes Cx transpose. In other words, it became X transpose C transpose. So it became X transpose C, and C is a scalar, so it can come before the vector. So it became Cx transpose. And we have this. And also the same here. Now the C's are the scalars, so I can bring them out. I have C squared here, also C squared here. They cancel each other. I will end up with the Rayleigh-Ritz quotient again of X, right? That's one. By the way, where do we see this Rayleigh-Ritz quotient? Can you guess? Can you guess? We see it in PCA, Principal Component Analysis. An example. Just an example of many. Where in PCA A is what? We'll see that, but I'm just giving you a heads up. In what? X is will be the features of the model, the data. What will A be in PCA? We'll see that. Just a heads up. Eigenvalue? No, it will be covariance matrix. Covariance. A will be covariance matrix. And as you see, we said A is symmetric, and also for this to either face up or face down, A must be either positive semi-definite or negative semi-definite, and we know covariance matrix is a positive semi-definite by definition, right? Interesting. Okay.
Years ago, and how they can be applied in machine learning.
So I don't know really. The question is, how did they come up with? Maybe it has a lot of functionality in different fields of science. It's just not for machine learning. They proposed this. I don't know how they came up with that, but yeah, then later it was used in machine learning. And we have now, let's minimize or maximize the Rayleigh-Ritz quotient, right? As I said, always machine learning is optimization plus some small other things, right? So minimize or maximize these with respect to X, right? So, but now also we can say this is equivalent to this, minimize or maximize the Rayleigh-Ritz quotient subject to this, the L2 norm of X is 1. Why? Proof is here. Let's prove it. Consider Y. Y is what? The normalized X. So its length is 1. X over L2 norm of X. Okay. Then let's consider the Rayleigh-Ritz quotient of Y. So we'll have Y transpose AY over Y transpose Y. Then replace Y with its definition. Again, L2 norm of X is a scalar. They come out. They cancel each other. You will end up with Rayleigh-Ritz quotient of A and X, right? And also consider this. So this was on the one hand. On the other hand, you will have a squared L2 norm of Y. What will it be? This scalar will be squared because I have squared, right? So I will have this squared times this itself became L2 norm squared, right? So these two cancel each other. So it becomes 1. Therefore, when squared L2 norm of Y is 1, the L2 norm of Y is also 1. It can't be negative 1. Why? Because it's norm, according to the properties of the norm that we discussed, right? Now, as you see, consider minimization or maximization of Rayleigh-Ritz quotient of Y. This subject to this, right? Now just change the name of the variable to X again. You will end up with this. So this Rayleigh-Ritz quotient of Y should be optimized subject to this. Did you see where the constraint came from? It's because of the definition of Y, right? Now I change it back. Change the variable. This is a dummy variable. You know what dummy variable is in mathematics? It means that the name of the variable is not important. We have a lot of dummy variables in mathematical expressions. An example is what? This. Summation of xi, I goes from 1 to n, for example. I is a dummy variable, right? We can say summation of x Benjamin. Benjamin goes from 1 to n. So whatever. So these are dummy variables. We don't care about their names. Y here is a dummy variable. Change it back to the name x. You will have this. Okay. Another equivalent optimization form for that Rayleigh-Ritz quotient is this. What is the difference here? Rather than minimization or maximization of the Rayleigh-Ritz quotient, I only consider its numerator, X transpose AX. Then, why is it equivalent? Can you tell me? Consider this, that we had equation 52. What does this mean? According to the famous formula that we talked about last session, it's X transpose X equals 1, right? Put it back in the, what is this? The denominator of the Rayleigh-Ritz quotient. So the denominator is 1. Therefore, we'll end up only with the numerator. Okay. The constraint in these equations 52 and 53 can be equal to any constant. So rather than 1, put anything you want. So here, rather than in the definition of y, put any c. So you don't care in this the constraint what it is equal to. It can be equal to any scalar. Here, for example, 1. Okay, so far clear? Now we define, let's generalize the Rayleigh-Ritz quotient, and we call it generalized Rayleigh-Ritz quotient or generalized Rayleigh quotient. And that's it. How is it different? Now in the denominator, rather than I having x transpose x, I have x transpose bx. So I'm having another matrix B. Numerator is the same as before, but in the denominator, I have x transpose bx, right? Where both A and B are symmetric matrices, X is non-zero vector because I don't want to have division by 0. And here, okay. What is an example of generalized Rayleigh-Ritz quotient in machine learning? Just a heads up, we will cover it. But can you guess? What? Support vector machine? No. But that's fine. That's fine. Give me guesses.
VLS.
What?
VLS.
VLS. What?
Partial least
Partial?
Partial least square.
Partial least squares, you said? But I didn't get it. PLS, right? I should think about that. What algorithm that is. I don't know all algorithms in machine learning, but no, that's not what I have in mind. Maybe I should see what PLS is. Have you heard of Fisher criterion? So in Fisher discriminant analysis, some people call it linear discriminant analysis, although they are slightly different. This is a Fisher criterion, actually, where Fisher criterion is exactly a generalized Rayleigh-Ritz quotient, where A is, what is A and what is B in that Fisher criterion? In Fisher criterion, A is the between scatter. What do I mean by between? The covariance between the classes. Okay, between classes. B is a within scatter. The covariances of the classes themselves. By the way, this is just a heads up. I will cover the whole details of them. That's it. So A is the covariance between classes. B is the covariance within classes, inside the class. Okay, let's write it down for you to remember. Between, sorry, and within, right? And interestingly, both these are scatter or covariance matrices, so they are symmetric and also positive, right? Now you see the beauty in Fisher criterion. In Fisher discriminant analysis, we maximize this criterion. Why? If we maximize this, can you give me your guesses what happens? When you maximize a fraction, it means you are maximizing its numerator and minimizing its denominator. Now, let's go one by one. Maximize a numerator. Maximize x transpose SVX. What does it do? What is x transpose SVX? It's kind of saying what is the covariance between the classes, how distant the classes are from each other. When you maximize that, what does it mean? What? Leads to all? No. So what was the other? So what you're saying, Simon? Exactly, maximize. So maximize this, it means maximize the distance between the classes. So push the classes away from each other. Right. Now let's go to the other way around. So now we can also see it as the minimization of the denominator. What is the denominator? The distance, kind of distances or scatter or variances of the points inside each class. When I minimize that, what does it mean? Exactly. So I make every class condense to each other. I push them toward each other. I think simply understand what does it do. So at the same time, I'm pushing the classes away from each other. I'm pulling the points of every class toward each other. So the classes become discriminated. If they were confused, they become discriminated. That's the reason. It's very interesting, right? This Fisher criterion was proposed, I think, in the middle of the previous century. Okay. So if the symmetric B is positive definite, it has a Cholesky decomposition. You know, what is the matrix decomposition? Nothing complicated. When you have a matrix, there are several algorithms for matrix multiplication. Simply means that write that matrix as a multiplication of several other matrices, right? We have various matrix decompositions. I think two of them you already know a lot. You have heard of a lot. Like one of them is eigenvalue decomposition. The other one is singular value decomposition. We'll briefly see them. One of them is Cholesky decomposition. However, for Cholesky decomposition, the matrix needs to be symmetric and positive definite. So as it is, then I can write it as C transpose. And according to Cholesky decomposition, C is a lower triangular matrix. What do I mean? It's a triangular matrix where the upper triangle is 0, right? In case B is positive definite, the generalized Rayleigh-Ritz quotient can be converted to a Rayleigh-Ritz quotient in this way. So the generalized Rayleigh-Ritz quotient of A, B, and X becomes the Rayleigh-Ritz quotient of D and C transpose X, where D is C inverse A, C inverse transpose. By the way, you know what this means, right? Inverse the C and then transpose it, or vice versa. Transpose it and inverse, okay? Well, the Cholesky decomposition, the algorithm, I don't explain the algorithm of Cholesky decomposition. It's out of the scope. It's in linear algebra. Don't worry. Look at it as a black box, okay? You understood decomposition or no? So decomposition is, I have a matrix B. I make it, write it as a multiplication of several other matrices, such as B1, B2, B3, whatever. Okay, usually in matrix decomposition, also called matrix factorization, two names for one thing. In either matrix factorization or matrix decomposition, we usually have either 2 or 3. So we decompose them into multiplication of 2 or 3 matrices, usually. So for example, in eigenvalue decomposition, we factorize into 3. Singular value decomposition into 3. In Cholesky decomposition into 2. Okay. And again, don't worry about how we do the Cholesky decomposition. See it as a black box. But if B is positive definite, we can write it as this, as a lower triangular matrix times its transpose. Okay. Then I'm going to use that to tell you that why this is correct. If B is positive definite, the Rayleigh-Ritz, generalized Rayleigh-Ritz quotient can be written as a Rayleigh-Ritz quotient. So I have this. What is this notation, by the way? Ask me for everything in the lectures. If I don't want anything to be unclear. What does this? It means define. What? Definition. Definition, exactly, definition. So in computer science, they use this for definition. Also sometimes maybe this, def, right? In mathematics papers, they use this notation for definition. Okay, these are different notations. What? You mean this?
Sir, can you see the lower and the matrix? You explain.
Oh, see, yeah, okay. Lower, it means this. These have values. These are all 0. Okay. So I was talking about these. These are definitions. By the way, in computer science, sometimes they use this for assign to. So you should, by context, you should find out whether it's assign or definition. So D is defined as this: C inverse A, C inverse transpose. Now let's see the right-hand side, which is this. We start from this according to equation 48, which was the definition of generalized Rayleigh-Ritz quotient. Let's put C transpose X here. So we'll have this. We know that this transpose reverses the order. So I'll have X transpose C, right? What is D? I'm replacing it with its definition in equation 59, which is this. Also, I can write, so what is this, by the way? Can you tell me? This is C inverse transpose C transpose. So C transpose is here and C inverse transpose is in the definition of equation 59. Okay. Then I have X. By the way, in exam, I never asked for proofs. Okay. So I provide you proofs for you to understand. The exams will be like solving. You will see like some examples in the assignment. So I give you some data points and you use the algorithms to solve that. That's it. Okay. So here we have this, and also here this becomes X transpose C, C transpose X. Interestingly, this is so wait, you can consider, just give me a second. Yes, according to equation 57, interestingly, this is B, right? And these C and C inverse cancel each other. And these C and C inverse also cancel each other. You understand why they cancel each other? I think it was, if it was C inverse C, you would say it's identity, right? But why is C inverse also identity? Because it's a square matrix, okay? So give me, I think that's a good thing to note here. In parentheses, some note from linear algebra. So we have this identity, okay? For both when C is a square or rectangular. What do I mean by rectangular? Also called truncated. Truncated. Why? Consider this is C, this was a square. What do I mean by square? The number of rows and columns are the same. So here, this is C. I can truncate some of the columns. So get rid of some of the columns. It becomes like this. For both of these, this is correct. Our C inverse equals I. For this C should be, C is a square. So when you truncate C, then C inverse, that doesn't necessarily become identity. Okay, that's fine. And okay, another thing. If C is orthogonal matrix, what is orthogonal matrix? Nothing complicated. These are very simple. Just try to understand them and you will see they are very simple. Orthogonal matrix is that its columns are orthonormal. What is orthonormal? It means that, so you have, when two vectors are orthonormal, it means that each of them have unit length, and when you multiply, when their inner product becomes 0. In other words, there are unit vectors which are perpendicular to each other, right? So when columns are orthonormal, it means they are orthogonal, they are also normal, then we call the matrix orthogonal, okay? When the matrix is orthogonal, then C transpose equals C inverse, okay? As a result, in an orthogonal matrix, C transpose C is identity. Why? Because C transpose C is just C inverse C, and I just told you that C inverse C is I, right? What about C transpose? Of course, this becomes C inverse C inverse. However, this becomes I if there is a big if C is not truncated, right? If C is not truncated. Is it clear now? Okay. By the way, for more information on these things, you can take a look at the video of linear algebra by, I think, Gilbert Strang in MIT. He recently retired. So truncate means that assume these are the columns of the matrix C. Assume this is D by D. When you truncate, you get rid of some of the columns. So it becomes D by P, for example, where P is less than D. Okay. So when you truncate it, it will not be square matrix anymore. It will become rectangular. And why am I saying this? Truncating the matrix happens a lot in machine learning. An example is what? Whenever you have linear dimensionality reduction, you usually have truncation. So, for example, you truncate the matrix, the result of the PCA, for this to project to lower dimension, right? So you see that a lot in machine learning. Right? Yeah.
C transpose C.
So C transpose C. First off, it becomes C, if C is orthogonal matrix, it becomes C inverse C, and we know that C inverse C is identity, no matter what, for all matrices. What?
There was C transpose is truncated, or RC is, I mean, C is truncated. Like.
Because here I'm talking about the columns of the matrix. So I said the columns. Orthogonal matrix is columns are orthonormal. I didn't say the rows are orthonormal. That's the reason. Okay. By the way, I remember Gilbert Strang said that the matrix C. So here he said, I don't know why they don't call this matrix orthonormal matrix. By convention, scientists are call it orthogonal matrix, but its columns are orthonormal. He said that in his lecture. Just a funny thing I tell you, if you see my transcripts, I never passed any linear algebra course. I watched that on YouTube. I learned the whole linear algebra online. Okay, so that's the thing. So as I said, we just proved that, right? Okay. Similarly, one of the properties of the generalized Rayleigh-Ritz quotient is this. Like before, we proved that for the Rayleigh-Ritz quotient. Now for generalized Rayleigh-Ritz quotient. So we have R, AX, and C, A, B, and CX. Put it CX here, and then the C's are the constants, so they come out, they cancel each other. You will end up with a generalized Rayleigh-Ritz quotient of X. Correct? Again, we can minimize or maximize the generalized Rayleigh-Ritz quotient. For example, when it is Fisher criterion, we are maximizing that. Then, so again, we can write it as minimization or maximization of the numerator subject to the denominator equals 1. The proof is similar, and I think you know why I'm only minimizing or maximizing the numerator. Why? Because the denominator I said is 1, right? Okay. Okay. Now, the next thing is eigenvalue and singular value decomposition. Used a lot in machine learning, a lot. So, eigenvalue and generalized eigenvalue problems play important roles in different fields of science. I think they are the most important matrix factorization algorithms in the entire mathematics and physics and everything, including machine learning, physics, statistics, mathematics. In the eigenvalue problem, so what is that? What does it do? What does eigenvalue decomposition do? It simply says that I decompose it into some eigenvectors and eigenvalues, okay? So I will have some eigenvectors and what do eigenvectors and eigenvalues mean? Intuitively, I mean. When I have the eigenvectors of a matrix and eigenvalues of a matrix, what do I mean? What do they tell me? Okay, matrices usually have some directions in some space, okay? Eigenvectors are the important directions, I mean informative directions of the matrix. And eigenvalues show how much important that direction is, because the information of the directions are not the same. One direction has more information than the other direction, right? And these directions are orthonormal to each other. So the information of this direction is not contained in the information of the other direction. Okay. So intuitively, this is what eigenvalue decomposition is doing, showing you the important directions of a matrix and tells you how much informative in each direction it is. Okay. And an example is, let's consider the eigenvectors and eigenvalues of a covariance matrix. Okay. In covariance matrix, what is information? Variance, right? So the eigenvectors of the covariance matrix show you in which directions the data has most spread or variance in this space, right? And the eigenvalues tell you how much variant the data is in that direction. Okay, that's an example. The eigenvalue problem of a symmetric, by the way, we will say that we can also call it eigenvalue problem. The eigenvalue problem of a symmetric matrix A, so it is symmetric, must be symmetric, is this, defined as this: A phi I equals lambda I phi I for all I from 1 to D. So phi i's are the eigenvectors and lambda i's are the scalars, and they are eigenvalues, okay? Eigenvectors and eigenvalues. And I have D of them because matrix is D by D. Also, I can write it in matrix form in this way: A phi equals phi lambda, where phi has the eigenvectors as its columns. So stack the eigenvectors column-wise, you will have a D by D eigenvector matrix. Also, we can have a matrix lambda which is diagonal, and you put the eigenvalues on the diagonal of that matrix. That also becomes D by D, right? Okay. What?
You see loss function?
No, we usually will see that. I think in this lecture, I guess I will show you that in specific optimization problems, they will always reduce to an eigenvalue problem. Okay, and we use those specific optimization problems a lot in machine learning. This means for all. Why? It's just reverse A. All starts with A. What is this? What is this notation? There exists. Because this is a reverse E. Exists starts with E. And this means there exists at least one, right? What if I want to say there exists only one? They show it in this way. These are notations of mathematics. It means that only one. There exists only unique one. Okay. So, yeah, always ask me for notations if you don't understand anything. Okay. So now this was the eigenvalue problem, right? Now right multiply the size, because when you have matrix multiplication, it's important whether you are left multiplying or right multiplying. Right multiply the size of the equation by phi transpose. This indeed. We know that phi, by definition, is an orthogonal matrix because eigenvectors are orthonormal. Therefore, phi transpose is I, according to just what I said a few minutes ago. So we'll have A equals phi transpose. We know phi is an orthogonal matrix, hence it is phi transpose is phi inverse. So you can also write it as phi lambda phi inverse. This phi transpose or phi lambda phi transpose or phi lambda phi inverse, doesn't matter. This is called eigenvalue decomposition. And as you see, the matrix A is decomposed into the multiplication of three matrices. Watch this, right? Do you see that? Okay. And yeah, I think I already explained these two lines. And this is called eigenvalue decomposition, also called eigen decomposition. Some people also call it a spectral decomposition. Okay. So now I think you know the they say the category of machine learning is called a spectral dimensionality reduction, because they usually reduce to eigenvalue decomposition. Okay. Okay, so the generalized eigenvalue problem now. So we defined eigenvalue problem, now generalized eigenvalue problem. What is that? Of the two symmetric matrices. Now I have two matrices, A and B, is defined as this. A phi I equals lambda I, B phi I. And in I have D eigenvectors and eigenvalues. In matrix form, I can write it as A phi equals B phi lambda, right? Where phi is has the eigenvectors and lambda has the eigenvalues. This is called generalized eigenvalue problem. As you see, eigenvalue problem is a special case of generalized eigenvalue problem where B is one, identity. B is the identity matrix, okay? And this AB is called a pair or pencil in generalized eigenvalue problem. And this phi and lambda is also called eigenpair of this pair AB in the literature. Okay. Now we have some optimization forms of the generalized eigenvalue problem or eigenvalue problem. Let's see them. So do you remember we talked about Rayleigh-Ritz quotient? We also talked about eigenvalue problems. Now let's combine them. Let's combine them. So maximize the, what is this? This is the optimization problem for a Rayleigh-Ritz quotient, generalized Rayleigh-Ritz quotient. I have A and B. How can I solve it? Back to several slides ago. Lagrangian, yeah? Yeah, because it's constant optimization problem. Lagrangian is this, minus lambda, this. By the way, use of Lagrangian is kind of dominant in a statistical machine learning. We use that a lot. Okay, so here I have this. Now the Lagrangian form is this. By the way, why do I write minus lambda rather than plus lambda? Because this is equality constraint, right? In equality constraint, when you have equality constraint, you don't care about whether you write minus lambda or plus lambda. When it is inequality constraint less than or equal to in a minimization problem, then that must be plus lambda. Okay, because the sign of the dual variable is important for inequality constraints. Okay, for equality constraint we don't care much. However, when it is equality constraint, it gives us choice whether to put minus lambda or plus lambda. How do I choose? I do the reverse engineering. So I go what I want to end up with, I come back. So for ending up with what I desire, I should put minus lambda here. Okay. So I have this now. Take derivative, set it to 0. Always as high school. So do that. What is the derivative of this? Can you tell me? Let's practice derivatives of vectors a bit. After I tell you some, let's practice, and afterwards in the next lectures, I take derivative fast. But for this one, let's go with the details a bit. So I have phi transpose A phi. It's quadratic, right? We know that, for example, x squared is derivative when it is a scalar. X squared, its derivative is 2x, right? So when it is X transpose X, therefore it must be again 2X, but X here is a vector, right? When we have here, it is phi. Phi transpose A phi. So if it was phi transpose phi, it would become 2 phi. But now, let's add a page because that's important. I have phi transpose A phi. I know if it was phi transpose phi, it would become 2 phi. Now it should become either 2A phi or 2 phi A or 2A transpose phi or 2 phi transpose A or something. Let's consider all of the combinations. Okay, what is phi? It is D by 1. What is A? D by D. What is phi transpose? 1 by D. Here it is D by D. It is D by 1. It mathematically makes sense. Here it is D by 1. This is D by D. It's nonsense. A transpose is D by D. This is D by 1. Makes sense. This is 1 by D. This is D by D. This also makes sense. Now, among these three, which one should we use? So, let me think. Yes, here we have used A phi, but give me a second. A transpose. Yes, I think for that we need to do this. So consider this. Just give me a second. Three by 1. Let it be 5 by 3. Why do I do that? See, consider this technique. I came up with this technique myself almost by trial and error during my PhD. Okay. So when I have phi transpose A phi, here I say phi, let it be 3 by 1. Doesn't matter, something. Okay. Then A phi, for this to make sense, it needs to be something by 3. Here, of course, it must be 3 by 3 for this, the whole thing to make sense. But only consider it partially. Why do I put 5 by 3? Because I want to discriminate these two. If I say 3 by 3, I don't know which 3. First 3 by, okay. So I have this. Then, if I do this, now let's go back to these dimensionalities again. This becomes 5 by 3, 3 by 1 makes sense. What about this? A transpose becomes 3 by 5. Phi is 3 by 1. Doesn't make sense. I reject this using this technique. Okay. Yeah, something like, thank you. So here, also it becomes 1 by 3. This is 5 by 3. This is also rejected. As you see, this is the correct answer, and this is exactly what we have used. Okay. That's a technique for taking derivatives in matrices and vectors. Also, so similarly, we'll have 2 lambda minus 2 lambda. Lambda is a scalar, right? It comes out of the derivative. 2 lambda, and then we'll have b phi, right? Set it to 0, you will have this. Now I think you understand why I put minus lambda, because I want this lambda to be positive here. Okay, so what is this? We just saw it a minute ago. That's the generalized eigenvalue problem of AB, right? So whenever we have this optimization problem, it's just the solution is what? The solution is we want to find phi, right? What is the solution? The eigenvectors of the generalized eigenvalue problem A and B, right? So whenever you have this, the solution is just the eigenvectors. Phi is the eigenvector here, right? The eigenvectors of the generalized eigenvalue problem A and B. Optimization form 2. Maximize this trace of phi transpose A phi subject to phi transpose B phi equals I. Just one thing in parentheses, let me tell you, I forgot. If you don't want to use this technique, you can go to matrix cookbooks with 1,000 pages. You look them, it's like a dictionary. You go and find the formulas for derivatives of vectors and matrices, okay? Or use the technique like, okay. So optimization form 2 is this: maximize trace of phi transpose A phi subject to this. In this case, I'm using trace. Why? What's the difference between equation 69 and equation 68? In equation 68, I only had one phi. So phi transpose A phi would be scalar. But now phi is a matrix. So it becomes trace of phi transpose A phi, right? And subject to this equals I. Now, again, this is a Lagrangian. For the constraint, I have, this is the constraint, right? My dual variables, or the weights that I talked about in Lagrangian, is this lambda transpose, okay? Then for this to become a scalar, because I'm multiplying them together, and this is also a scalar, I have to have a trace, okay? This lambda is diagonal. Why? For proof, see the appendix of my tutorial named Eigenvalue and Generalized Eigenvalue Problems tutorial. Okay, that's available in archive. If you want to see the proof why lambda is diagonal matrix, you can see that. Okay, then, so it's a diagonal matrix. And then you take derivative, set it to 0. If you do that using the technique, you will end up with this. What is this? Again, generalized eigenvalue problem. But now, this time I have several eigenvectors. Phi is a matrix of eigenvectors, right? Therefore, when we have this, the optimization problem is matrix phi, right? Then the solution is the matrix of eigenvectors of the generalized eigenvalue problem, A and B. Okay? Optimization form 3 is this: minimize the L Frobenius norm of x minus phi transpose x, okay, squared, subject to this. We see that a lot. What is this? Can you tell me? Can you guys tell me? Let's analyze it. So I have x. What is phi transpose x? We saw it in previous session. What was u transpose x? It was reconstruction of x after linear projection, right? Do you remember? If you don't remember, see the previous session. What was linear projection? U transpose x. What was reconstruction after linear projection? U transpose x. Now rename u to phi here. Doesn't matter. Okay. So it's, what is this then? Mean squared error of what? Data and its reconstruction. So it's the residue that we talked about. The residue or error of reconstruction. The reconstruction error. So I'm minimizing the reconstruction error subject to some constraint. This is exactly the optimization problem of PCA. So you can see PCA as these two. Now I think you understand why PCA's solution is the eigenvectors of covariance. That's the reason. Okay. Now, so x is d by n. And by the way, please focus on my calculations, because these calculations will be repeated a lot. And when you understand it once, the whole course becomes easy for you. Okay. So what is this? Squared Frobenius norm. Do you remember the formula that we had in previous session? In my courses, preliminaries are the most important parts of the course, okay? Because I refer to them a lot. You remember the preliminaries of the previous session? The formula of quadratic form. I said Frobenius norm of Benjamin squared is Benjamin transpose Benjamin. Do you remember? But if Benjamin is a matrix, I need to have a trace also. Okay, so I have trace of Benjamin or this transpose Benjamin, right? And I know that when I have this, so the first element transpose minus the second element transpose, but the second element matrix multiplication, it reverses the order, right? Also have this. Now I have this. I can multiply the terms to each other. The first by first, first by second, second by first, second by second. So I'll have 4 terms. Do you agree? You understand what I'm saying? You do follow me. So I mean simply this: AB times C plus D becomes AC plus AD plus BC plus BD. Okay. So here, therefore, I have 4 terms. Interestingly, phi transpose phi appears here. And in constraint, we said it must be 1. So this goes away. Then we'll have this. What is this? X transpose phi transpose X. We also have minus 2 X transpose phi transpose X. So we'll have only minus 1 of them. We know trace is a linear operator, so I can apply it to its elements. Okay. Then here I'm using the cyclic property of trace. What is that? Very easy. Nothing complicated. So it's this. Trace of A, B, C. When you have matrix multiplications in trace, you can change the order. So you can bring any of them to the other side. So what do I mean? It's equal to trace of CAB, bring C here. Then bring B here. What is that? Equals trace of BCA. Then bring A again here. It's equal to trace of ABC. Did you understand? As you see, it's like a cycle. They call it cyclic property of trace. So according to the cyclic property, I can bring this X here. As you see, we can apply cyclic property several times. So I can bring, I'm not shuffling the elements. I'm just bringing them back, right? Then I can write it as the trace of the whole thing, right? Now I simplified the cost function, the objective function, subject to constraints, right? The Lagrangian is this, right? Take derivative, set it to 0. You will end up with the. Now, I define X transpose to be a new matrix A. This is exactly eigenvalue problem. Therefore, the solution of phi, the solution of this optimization problem, is the eigenvector of X transpose. Right? You understand? And X transpose, I will explain it more when it's time. It's just a covariance matrix when data is centered. So basically, it's saying that this the solution of this is the eigenvectors of the covariance matrix. Again, I emphasize that I don't want you to panic at all. I never ask these proofs in exam. You will see the sample questions in assignments. They are very easy. Okay. I'm explaining this for you to understand the algorithms. Okay. Now we had phi here, only one vector. Let's make it matrix. Let's make, yeah. We will use them a lot during the course. This is just preliminary. Yes, yes. We will see, for example, in different algorithms, this is just a general form, right? Then, for example, in a specific algorithm, I will tell you what we should put as X, what we should put as phi, right? So whenever we go to a new algorithm, we'll see that we will formulate it and we'll end up with some optimization problem. And we'll see, by the way, it's in the form of what we saw in the preliminaries. Something like that, right? Okay. I haven't yet started the course. This is preliminaries. Let me go faster and start the course. Okay. So phi is the matrix. Now, if we solve it, similarly, it becomes this. The Lagrangian is this. Take derivative, set it to 0. We'll end up with this. And that's the eigenvalue problem of A. Now, optimization form 5. Maximize this. What is this? Generalized Rayleigh-Ritz quotient. We can write it. We saw that it's equivalent to this in the previous slides. The Lagrangian, take derivative, set it to 0. We'll end up with this. That's the, again, generalized eigenvalue problem, A and B. So you see, we have different optimization forms. They end up almost to the same thing. Which one? These? So we said that here, I'm saying that let the denominator be 1. Therefore, rather than saying maximize the whole fraction, I'm just maximizing the numerator, right? We proved this equivalence for Rayleigh-Ritz quotient, but similarly, you can prove it for generalized Rayleigh-Ritz quotient. Okay, we talked about optimization forms and eigenvalue problem and this. Now let's talk about singular value decomposition. The second most important decomposition in machine learning. Okay, so the first one was eigenvalue decomposition. This is singular value decomposition, or SVD, is one of the most well-known and effective matrix decomposition methods. There are different methods for obtaining this decomposition. One of them is Jordan's algorithm. We don't go into how we do the decomposition out of the scope of this course. That's in linear algebra. We're going to use it. So SVD has two different forms, right? Complete or incomplete. First off, one major difference between eigenvalue decomposition and SVD is that SVD, we can apply SVD on rectangular matrices also. But eigenvalue decomposition is applicable only to square matrices. Okay. So consider A to have alpha rows and beta columns, right? Then I can write, this is the SVD. So U sigma V transpose, right? U is in, when we have complete SVD, U and V are square matrices. U is alpha by alpha, V is beta by beta, then sigma must be alpha by beta, right? Sigma is a diagonal matrix, but a rectangular diagonal matrix here. What do I mean? It's either in this case or this case, depending on whether alpha is greater than beta or not. So this is the diagonal, or this is the diagonal. The other elements are 0, right? This sigma, so the U is called the matrix having the left singular vectors. V is the matrix having the right singular vectors, and sigma is the matrix having singular values. Okay? Understand? Because it came left in the SVD. Here, it is left. V came right, so we call it right singular. So now we have two vectors. In eigenvalue decomposition, we had only one eigenvector because it was a square matrix. Now it is a rectangular matrix, so we have left and right singular vector. Now, incomplete SVD. Incomplete. So consider this again. Now U and V are rectangular, but sigma is a square. So U is alpha by K, V is beta by K, and sigma is K by K. Okay, where K is usually minimum of alpha and beta. Okay, and here sigma is the a square diagonal matrix. Okay. Interesting. I already talked about this, but now in SVD. In SVD, by the way, U and V in SVD are orthogonal matrices. Okay. So U transpose U equals U inverse U. So it's identity. V transpose V equals V inverse V is identity. What about U transpose? It's U inverse. If it is not truncated, it's I. What about V transpose? It's V inverse. If it is not truncated, it's I. Okay. There is relation between eigenvalue decomposition and singular value decomposition. No wonder why they're both important. So in both complete and incomplete SVD of a matrix A, doesn't matter which, the left and right singular vectors. So the left singular vectors are the eigenvectors of A transpose. The right singular vectors are the eigenvectors of A transpose A. Okay, I will prove it for you. And the singular values are the square root of eigenvalues of either A transpose or A transpose A. Did you get it? The proof, I think, clarifies everything. Consider A transpose. Okay, A transpose. Rather than A, I replace A with its singular value decomposition, SVD. So I will have U sigma V transpose and U sigma V transpose transpose. We know that transpose in matrix multiplication reverses the order. So I will have V sigma U transpose. I will have these two. Interestingly, I have V transpose V in between, which is identity. It goes away. It simplifies to this. U sigma sigma U transpose. What is sigma sigma? Is sigma squared. Right? So you have U sigma U transpose. What is this? What is U sigma squared? Assume sigma squared, rename it to whatever, something like, I don't know, B, C, D, whatever. U, D, U transpose. What is that? This is eigenvalue decomposition. Right? Rather than sigma squared, put lambda. Just a few slides ago, we talked about eigenvalue decomposition. We started with A transpose, replaced A with a singular value decomposition. We ended up with the eigenvalue decomposition of U sigma squared U transpose, right? Therefore, U here is the eigenvectors because U sigma squared U transpose is the eigenvalue decomposition of A transpose. We just proved that, right? Therefore, U is the eigenvectors of A transpose. On the other hand, U was the left singular vector. Okay, now the other way around. By the way, here, also sigma squared is the eigenvalues of A transpose. On the other hand, sigma itself was the singular values. Therefore, singular values are the square root of eigenvalues of A transpose or A transpose A, right? Now also let's take a look at A transpose A. Similarly, we have this. We replace A with its SVD. We'll have this. Interestingly, U transpose U appears in between, which is I. It simplifies to this. We'll have V sigma squared V transpose. Again, that's another eigenvalue decomposition, whose eigenvectors are V. So V is the eigenvectors of A transpose A, and sigma squared are the eigenvalues of A transpose A. Did you understand the relation of SVD and EVD or eigenvalue decomposition? Here, V was also the right singular vectors of A. Okay. Acknowledgement. Some slides are based on our textbook elements of dimensionality reduction and mindful learning. Also, some slides of this slide deck, the expectation parts, are inspired by the lectures of Professor Mu Zhu at the University of Waterloo Department of Statistics. For more information on optimization, you can refer to my course Optimization Techniques on YouTube channel. Also, for more information on Rayleigh-Ritz Quotient, eigenvalue problem, and SVD, you can see this tutorial paper, eigenvalue and generalized eigenvalue problems tutorial. Okay. More information on expectation. I have 2 tutorial papers, the theory behind overfitting, cross-validation, regularization, bagging, and boosting tutorial, and also sampling algorithms from survey sampling to Monte Carlo methods tutorial and literature review. These are optional. Okay. These are references. Why do I show the references? Because I hate when I watch a YouTube video and they say according to reference something, and at the end they don't show the references. Okay, so let's have a break and come back at 18 to, I think, am I right? 18 to 9. What?
8:45.
8:45. For 8:45, that's fine. 8:40. Okay. Okay, so I asked you guys, I don't know whether you saw the announcement, to please watch the video overfitting, cross-validation, regularization on my YouTube channel. So I go a bit faster on these slides. But if you haven't, if you are watching on YouTube, go and watch that YouTube video. But if you here haven't watched that, that's fine. I also try to cover as much as I can here, but you would understand better if you have watched that video with more details. Measures for signal. First, here, consider a learning model. So we have some data points, right? We have something, and xi is the ith data point. Right? And fi, let it be f of xi. So I feed xi to the learning model, I get fi or f of xi. And as you see, this is the ideal model f, and this gives me f of xi, fi. I never have this ideal model. So it's a bit related to philosophy. So it's related to the philosophy of Greek philosophy, the philosophy of Plato, his theory of forms. So theory of forms by Plato in ancient Greek philosophy says what? Says that whatever we have in this world has some true idea or form in some other world, the world of forms, right? And for example, we have a true human there. We have a true rooster there, right? And we are just instances of those true things, right? This is a big issue in the philosophy of epistemology, okay? Doesn't matter. As you see, it's kind of related. We have a true learning function. You never have it. You hope to imitate it somehow. So you have a true model, and you have f hat, which tries to imitate that. And you have training data, you feed to f hat, you will get yi hat, right? The output for corresponding to an xi. But the true thing is fi. So you want yi hat to be as close as possible to fi, right? And we know that the labels that we have for training data, let's call them yi, right? Yi is not exactly fi. It's fi plus some noise. What if my training data is noisy? We never know that what was the true fi. That's in the other world, right? According to Plato, for example. And so yi is fi plus some noise. epsilon I, right? And epsilon I is the Gaussian noise with mean 0 and with some the variance sigma squared. Why is its mean 0? Because in the noisy thing should be around the Fi itself. You shouldn't change the mean. The mean of the noise should be 0. So the mean of Fi plus epsilon I becomes the mean of Fi. Okay. Now I have this, and I know epsilon I is this. According to this, expectation of epsilon I is 0. Its mean is 0. Expectation of epsilon I squared. What is that? Recall preliminaries. The definition of variance. I restate that. So I can write it as variance of epsilon I plus expectation of epsilon I squared. What is this? This is 0. What is this? Sigma squared. The variance of epsilon I is sigma squared, right? According to this. Now, also, I know that expectation of Fi is Fiy because Fi is not random. Fi is the output of true model. True model is not random. Okay, so expectation of Fi becomes itself Fi. And so, yeah, I think I already explained these. Now, this learning model, by the way, can be any model, classification model or regression model, prediction model, right? Can be any model. And these Yi's hats are the predicted outputs or predicted labels, right? For Xi. So again, recall preliminaries. Mean squared error of F hat equals variance of F hat plus bias of F hat squared. I can also write it in this form to write it as a Pythagorean theorem, right? Using a triangle. So you will have a triangle with orthogonal angle, and we have bias of F hat here, square root of variance of F hat here, and a square root of mean squared error of F hat. Why is it mean? And here, therefore, we can have F and F hat. Well, because this is a difference of F and F hat, mean square root of mean squared error of F hat, right? Also, you can see this as expectation of F hat according to that formula of variance. Recall preliminaries. And what is this? Bias, according to the definition of bias. Definition of bias is expectation of F hat minus F. Remember? F itself. Okay. Mean squared error of the estimation of the observations. Now, suppose we have an instance x0, y0. So I have some instance x0 and its label y0. And if it is a regression problem, the label is continuous. If it is classification problem, the label is discrete, right? Okay. This instance, we have two cases. It's either training data or test validation data. So when I say training data, it is in the training data set. If it is test or validation data, we don't use that during training, right? We don't use that in training. Okay. According to equation 1, do you remember we said yi equals fi plus some epsilon? Here I can say y0 is f0 plus epsilon 0, right? Assume the model's estimation of y0 is f0 hat. Okay. You can call it y0 hat, doesn't matter. Y0 hat or f0 hat. The model's estimation output. The mean squared error of this estimation is what? Expectation of, this is the definition of mean squared error, right? Expectation of f0 hat or y0 hat, doesn't matter, minus y0, actual y0, right? Squared. Now, according to this, I put it here. So rather than y0, I put f0 plus epsilon 0 according to equation 5. I'll get this, right? Now I use the binomial equation. What do I mean? A minus b or a plus b squared is a squared plus b squared plus 2ab. If I do that, so consider this as the first term and this as the second term. This is squared plus this is squared minus 2, the first one times the second one, right? expectation is a linear operator. So I will have the expectation of the terms. Then what? Then I have here, what is expectation of epsilon 0 squared? I just proved that here in equation 2. Expectation of epsilon I squared became sigma squared. Okay, so let's use that. It's this, right? Minus 2. So the other things are the same as before. Now the last term, consider this last term. Let's discuss the last. Okay, so I'm writing it here without minus 2 behind it. Okay, according to equation 5, which is this, rather than epsilon 0, I can restate it, right? I can say epsilon 0 is y0 minus f0. So rather than epsilon 0, I put y0 minus f0, right? And this is the same as before. For calculation of this term, we have two cases now, as I said, whether the instance x0, y0 is in the training set or not in the training set. Okay, let's see. Case 1, instance is not in the training set. So it's either validation set or test set. Okay. Not in the, therefore, y0 is not in the training. Then this means that the estimation f0 hat is independent of the observation y0. Right? Because the observation was not used to train the model. When you never use the observation to train the model, then f0 hat is the estimated output for x0, right? You never used x0 for training. So f0 hat will not depend on y0. Because y0 is for the model. You never use x0 for training. Therefore, what in this case, x0 and f0 hat are independent. This means independent, okay? This means perpendicular. This means independent. What is this notation? It's therefore. Therefore. Therefore, in mathematical language, okay? Therefore, then now subtract from the sides minus f0. So y0 minus f0 is independent from f0 hat minus f0. Okay. As a result, do you remember? Now we are discussing this equation 7 in both cases. In this case, what happens? As these are independent, expectation of multiplication of two independent terms becomes the multiplication of expectation when they are independent. So expectation of the first one times the expectation of the second one. What is this? So this, I'm repeating it here. Okay, that's okay. And now let's talk about this. Consider this. Expectation of y0 minus f0. Expectation is a linear operator. I can say expectation of y0 minus expectation of f0. What is expectation of y0? Let's see. I know, I'm going hierarchically. Doesn't matter. Expectation of y0. What is that? According to equation 5. What was equation 5? This. y0 was f0 plus epsilon 0. According to equation 5. Take expectation from the sides. So we'll have expectation of y0 equals expectation of f0 plus expectation of epsilon 0. Expectation of f0 is f0. Why? Because the model f0 is not a random variable. What is expectation of epsilon 0? 0, because noise has mean 0 mean. Right? Therefore, you have f0. What? Because, do you remember I said that? So assume this is the data. You add some noise, then you will be somewhere around here. If the mean of the noise is not 0, for example, here, then that radii will be here. You will not be around your point at all. I want to be around my point. So I want the mean of data plus noise to be equal to the mean of data. Therefore, the mean of noise must be 0. Otherwise, I will have a shift. Okay. So far clear. Now, in this case, the last term in this equation 6, this. So here, expectation of y0, we found it is f0. So I'm putting it here, right? Interestingly, it became f0 minus f0. So it became 0. Now I put it back here. Rather than this, I put 0. 0 times this becomes 0. The third term in this case became 0. The third term in equation 7 here. This became 0 when the data is not in the training set. You might be wondering why we are doing this. You will see the beauty. Just bear with me for a few minutes. Okay. So this became this equation 6. This mean squared error, right? Became simplified to equation 8 in this case. Expectation of f0 hat minus f0 squared plus sigma squared, right? This is what we found. I'm repeating it. Now assume we have we have m data points which are not in the training set. So m test points or m validation points. We know that I can write expectation as I can approximate it as the average. Do you remember Monte Carlo approximation? So I can say 1 over m summation of fi hat minus yi. Now, rather than 0 f0 y0, I'm having I goes from 1 to m, right? So I have m of them. Also, this expectation, I can have the Monte Carlo approximation, right? And then sigma squared, right? Now, I multiply the size by m. So I will get this. So far clear? Okay. This term, the first term, this term is the error between what? Between the predicted output and the label in the dataset. Because this is the predicted, this is the label, right? So it's the empirical error. We denote it by a small error. We call it empirical. I'm naming it empirical error. What is this term? The error between the predicted output and the true label, which we don't know. Okay? Therefore, we call it true error, denoted by capital error. So basically, equation 9, you can write it as empirical error equals true error plus m sigma squared, right? We can restate it as error, rearrange the terms, true error equals empirical error minus m sigma squared. This m sigma squared is a constant, right? It's constant. It can be ignored. Let's drop it. Just, okay, I don't care. Therefore, what does this mean? The empirical error in this case is a good estimation of the true error when the data is not in the training set. Okay. Now let's go to the other case. Case 2. Now the data instance is in the training set. It is actually a training data point. Okay. For this case, we need to use a mathematical formula named SURE. Okay. S-U-R-E. SURE is short for Stein's unbiased risk estimate. Okay. It's a mathematical. That's one thing in the statistics. Okay. So what is that? For more information on SURE, see our tutorial 2, which is the theory behind overfitting, cross-validation, regularization, and bagging and boosting. Doesn't matter. So here, there is consider in this slide here, I'm gonna tell you about the Stein's lemma for sure. What is that? Consider this vector mu d-dimensional. Okay, I'm saying this in parentheses. Consider a vector mu. Also, a vector g of z, g1 to gd. It's a function applied on a vector z. Okay, and so g of z gets a d-dimensional vector and outputs a d-dimensional vector, right? And this equation 11 is called Stein's lemma. For proof, see the appendix of that tutorial. Okay. This is this is a formula, and we are going to use that. If the random variable here, z was a random variable, but it was multivariate. It had d dimensions. If it is a scalar random variable, then this equation 11 is simplified to equation 12. Okay. This is a Stein's lemma for a scalar. So I'm repeating it here. Now I've closed the parentheses. I'm going to use this formula. Okay, so here, in our case, let's take, rather than z, I put epsilon 0, the noise. Rather than mu, I put 0. Rather than g of z, I put f0 hat minus f0. Let's put them, all of these, in the Stein's lemma in its left-hand side. Then you will get expectation of epsilon 0 minus 0 times f0 hat minus f0. Why did I do that? Why did I choose these? Because this, according to my memory, if I'm not wrong, exactly, this was equation 7. I tried to make the left-hand side of a Stein's lemma the equation 7 that we had. Okay. So now this according to the Stein's lemma, it's equal to this, right? Now let's simplify this right-hand side of the Stein's lemma for our case. We know expectation is a linear operator. So, by the way, sorry, this is so derivative also is a linear operator. Derivative of f0 hat minus f0 with respect to epsilon 0, you can say it as derivative of f0 hat with respect to epsilon 0 minus derivative of f0 with respect to epsilon 0. Right? Now what happens? What is derivative of f0 with respect to epsilon 0? Can you tell me? What is derivative? Derivative of a with respect to b means if we change b, how much does it impact a? F0 never changes. It's the true model. No matter, it doesn't care about the noise that we had, right? So it's 0, right? Therefore, it simplifies to this. Now we have now do the chain rule rather than, do you see, we are using the preliminaries a lot. So chain rule. So here, derivative of f0 hat with respect to y0 times derivative of y0 with respect to epsilon 0. Okay. Now, what is derivative of y0 with respect to epsilon 0? Remember, y0 was f0 plus epsilon 0. So its derivative with respect to epsilon 0 is 1. So this is simplified to 1. So it's simplified to this, right? Do you agree? Okay. Yes. So here now, let's put, so this is simplified to, let me think. So yeah, we had this. So we found this equation 7 became this. Now put it back in equation 6, the mean squared error. Let's go back several slides ago. This was the equation 7 was the last term in equation 6, right? We just found simplified that for our case. Let's put it back as this, and there are other terms we already had them. Equation 6 becomes this. Again, so I'm repeating it here, what we found. Again, I use Monte Carlo approximation. Now this time, assume my training instances, I have n training data points, right? Rather than 1 training data. So by Monte Carlo approximation, I can replace these expectations by their approximations, right? Also this, by its approximation. I multiply the size by n. I'll get this, right? Again, this term, what is this? This is the empirical error. What is this? This is a true error. because it's the difference from the 2fi. Therefore, equation 14 can be written as this. Empirical error equals true error plus n sigma squared minus some term. Rearrange the term, you will get equation 15. The true error equals empirical error minus something plus something, right? So I'm having it here. Okay. This term, again, you can see it kind of, you can ignore it. That the n sigma squared is a constant. However, is this constant? No. The last term here is a pain in the neck, right? So it means that, and let's analyze the last term. What is the last term? That's actually a measure of complexity or a measure of overfitting, right? I'll tell you what overfitting is, but for now, it's a measure of complexity or overfitting. Why? What is this derivative? Derivative of S. What is fi hat? The predicted output for xi. Derivative of that with respect to yi. My labels, my ith label, my actual. So it means that I have xi, yi in my training data. It's training, right? Xi and yi in this case is in the training set. So I have xi and it's labeled yi in the training set, right? I feed xi to my f hat, to my model. I never have f. F hat tries to be similar to f. It gives me some yi hat. So, or I named it fi hat, doesn't matter. Fi hat, right? I hope fi hat is similar to yi, but it not necessarily is, right? Then this derivative means that in the derivative of this fi hat with respect to yi, it means that let's change yi a bit, see how much fi hat changes. Let's see this in this example, figure below. Consider figure A. Consider this green dots. Do you see that? Consider. I change. So here, this is labeled yi. This is xi. So this is xi. Then this is the labels, right? I'm having a regression model. Assume the red line here is the output for my points. What do I mean? For example, for this point, its label is this, but its prediction label is here, right? Okay. So consider these points. I change its yi a bit. So I bring this a bit down. The green point, which was here, I brought it here, right? How much does the whole model change? A little bit. So it moves this line a bit down because it's in the training set. It affects f hat, right? So it brings us a bit down. Now consider these two figures, figure C and D. In this case, my regression model, my f hat is too complex. It has passed through all of the training data points. Consider this green point, change it a bit, like here. It modified the model very much. Now, consider C and D. Consider a point here. Here, it was predicting it up, but now it is predicting it down. By changing one of the training data points, the labels, the whole model predicts completely differently for the high x's here. So it means that I tweaked yi a little bit. It changed the model a lot. Therefore, it's a measure of complexity, also called overfitting, right? And why? Because why do we call it complexity? Because this model is clearly complex. It has passed through all of them. But this is too simple, right? As you see, when in the case where instance is in the training set, we have a pain in the neck term, which is a measure of complexity. Okay.
What are some real-world applications for case 1 and case 2?
So whenever we have a data set in the machine learning, we split it into usually 2 to 3, usually 3 sets. training sets, validation sets, and test sets. I will talk about it in a few slides. So when the data point is in the training set, it affects the model, as here. However, when the data is in the test or validation set, it doesn't affect the data. We will evaluate our model on that. Okay. And I'm still gonna use that to tell you why overfitting happens. I haven't yet completed my. And it can be any data. I'm talking about machine learning in general.
We have validation and test data.
Yes.
So which part data are you talking about?
No, you split your data. Assume you have 100 vectors. These vectors can be any feature vectors, right? You split that to 80 vectors for training, the 10 vectors for test, 10 vectors for validation. And then you use that you use the training points for training your model and those for evaluation of your model. Yes.
In the training set, I mean, this data can be from any part of data set?
Yeah, you shuffle the data and you randomly take 80% as a training. Yes. So now, we saw that. I'm going to use that to explain overfitting. But first, let me tell you underfitting and overfitting. If the model is trained in an extremely simple way, opposite of complex, we have underfitting. Okay. Underfitting is sometimes called as overgeneralization. Also, if the model becomes too complicated, we call it overfitting. So in underfitting, we have low variance, high bias, and low complexity. I will tell you what. In overfitting, we have high variance, low bias, and high complexity. So consider this. These 4 data points. Once I put a line, once I pass through all of them. Maybe. Okay. Of course, here this is underfit. This is overfit. As you see in underfit, the variance is low. We don't go much high and down, right? The variance is low. The bias is high. Why? Because I have a lot of error. The bias is high. In overfit, it's the other way around. The variance is high, go up and down. The bias is low. And in underfit, we have low complexity. In overfit, we have high complexity. By the way, these are asked a lot in interviews in the industry. If you are engineering, machine learning engineers, they will ask you these things a lot. Okay. So, yeah, I think I already explained this, that you change. So here, for example, if you change this a bit, it completely changes the behavior of the model. Here, it changes a little bit. It changes too less, not too opposite of too much. So here, you change it, it changes adequately. So this is overfit. This is underfit. This is good fit. We want the middle case scenario. We want a good fit. And let me tell you one thing. I think I have it here. Yes, I think I explain it sometime later. Okay, so cross-validation. It kind of relates to what you asked. So we have our data set D, okay, and I assume my training data set I denote it by T, and my test data set by R. This is my naming, doesn't matter. Okay, we can split the data into training and test data. In one of the ways to split the data is this. So I split it so that their union becomes the whole data and they don't have any overlap. Okay. here we are having, I'm gonna tell you about the cross-validation. And what is cross-validation? We have two types, at least two important types of cross-validation. And that's one of them is k-fold cross-validation, and the other one is leave one out cross-validation. I will tell you about this. In k-fold cross-validation, we randomly split the data set D into k partitions, okay? K disjointed partitions where their size is almost equal. Their union becomes the whole data, and they don't have any pair of them, don't have any intersection, overlap, okay? This, by the way, denotes the cardinality of the set, okay? Usually, the number of partitions is 2, 5, or 10 in the literature, but the most common case is 10. Usually, we have 10-fold cross-validation. If you write a paper and you say, I did 2-fold cross-validation, the reviewer will get suspicious that maybe you didn't get good result on 10-fold cross-validation, and you're reporting 2-fold or 5. Okay, that's fine. So its algorithm is this: randomly split your data D into k partitions with almost equal sizes for k from 1 to k. Then you get the kth partition, right? Each time you take one of the partitions as the test and the rest as the training. What is this notation, by the way? This is a subtraction or minus for sets. So it means the set D minus set R, okay? Then use the training set to train the model, okay? You should never here use the test set for training your model. And then evaluate on the test set. Of course, it gives you some error, okay? Why have I denoted by true error? Because as I said, the empirical error on the test data or validation data is a good estimation of true error, right? So it gives me the kth error. Therefore, I will have, if I have 10-fold cross-validation, I will have 10 test errors. Then I report the average error as the final error. I take the average of the errors. This is k-fold cross-validation. What is leave one out cross-validation? When your data, the number of data points is small, it doesn't make sense much to do, for example, 10-fold cross-validation. Because when you, for example, when you have 20 data points, you divide it into 10 partitions, or you have 10 data, sometimes you have too small. Your data is small. In this case, we use leave one out cross-validation. Simply, it means that whatever number of data points you have, let's call it n, okay? Then we'll have n iterations or n folds. In each iteration, you take one of the points as a test and the rest as a training, okay? Hence the name leave one out cross-validation. And then you report the average error again. We have two important cheatings in machine learning. Be careful about that. Many people do the cheating without even knowing. Okay, cheating number one. The test set and the training set should be disjointed, okay? They should not have any overlap. Why? Can you tell me? Because I'm not supposed, when I'm training the model, means that I'm preparing the model, I'm not supposed to have the test set, okay? The test set should come afterwards. Just consider this example, and I think it will make sense to you. I got a project from ministry to make a model for predicting, I don't know what, to do some traffic tasks on the intersections, okay? I got funds from the government, and I do some project, and I want to give them the project. This is the model is ready. They will install it on the street, and they will perform tasks. Okay, I can say I train the model with some data, with some training, and then after it gets deployed, it gets tested, right? Am I supposed to have the test data, which is after deployment, use that for training? Of course not. Logic says no. But when the test and training are not disjointed, they are contaminated, then we are actually doing this mistake. We are using that test, which is supposed to be after deployment. We are using that for preparing our model. And hence it's cheating. Right? If assume I do the cheating, I assume I test my model with my training data. Of course, it will perform very well because I use that for training. It will perform 90% accuracy. I tell the government, the ministry, it works very well. They deploy it on the intersection and we'll have a lot of accidents because it will work awful for unseen data. Okay, that's one. Also, validation set. In some cases, the model has some parameters which need to be determined. I'll call these parameters hyperparameters. So why? Because usually in machine learning, when we say parameters, we have learnable parameters, which are the optimization variables. We need to tune them. So for example, the weights of neural network. These are parameters also, which we want to learn. But the parameters that are chosen by user, such as learning rate and these things, I call them hyperparameters. Okay. So we have some hyperparameters usually, but we want to set them. How do we determine them? In this case, we will have a validation set, V. Then we split our data into 3 parts: training set, test set, and validation set. Usually, training set is larger than both validation and test set. So what do we do for this? Now, we can use this also in the cross-validation. Doesn't matter. Assume in cross-validation, do you remember I said, for example, you have 10-fold, right? You get 9 folds for train and 1 fold for test in each iteration, right? Now this time, rather than 9 folds, take 8 folds for training, 1 fold for validation, and 1 fold for test. Of course, they need to be disjointed again. Validation set, training set, and test set. And you can use validation for tuning your hyperparameters. I will tell you how. Assume I have some hyperparameters such as learning rate. I don't know what to put. Okay, I give some candidate choices. For example, assume my hyperparameter can be between 0 and 1, a float point. I choose some, I split this region into some choices, such as 0, 0.1, 0.2, 0.5, 0.7, 1, something like that. Okay. Then I will have a for loop over these hyperparameters, right? Then in each value, for each value of the hyperparameter, I do a cross-validation. And I only consider the error of validation set. Okay? The error validations. Then do you agree? So each hyperparameter value gives me an average validation error. Why average? Because I have folds of cross-validation, right? Then I can see which hyperparameter value gave me the minimum validation error. Then I set that hyperparameter to that value. Then I train my model once again with that hyperparameter value, and then I test it on the test set. Did you see? For determining the hyperparameter value, I never use the test set. If you do that, that's also cheating. Also. So, cheating number 2. So, training, validation, and test, they all should be disjointed. The validation set and test set should be disjoint because, again, I think it's obvious, yes? You are not supposed to have access to the test set. How can you use that for tuning your hyperparameter? Tuning your hyperparameter also affects the performance of your model. You're not supposed to use that. So that's also cheating. This type of cheating is used a lot. This mistake is done a lot, especially in deep learning. especially in deep learning. So why? Because in deep learning, training takes time. Usually people don't do cross-validation. Because in every cross-validation, in every fault, you have to train once. Maybe your deep learning training takes days. You can't do it for 10 times, right? Therefore, people do what? They split their data only to train and test. They make this mistake a lot, even in papers, to train and test. Then they play around with their learning rate, whatever. They see the test accuracy. They say, oh, this learning rate now is good. I choose that, and then I report the test accuracy. This is cheating. What should you do? Even if you don't want to do cross-validation for deep learning, that's fine. But it's still, you can avoid cheating. How? Split your data into train, val, and test, and do one fault. Do one fault. Only train once with several hyperparameter values, with several learning rates, but do not evaluate on the test set. Evaluate on the validation set and see the results. Okay, the minimum validation error, that's good. Let's set the learning rate to that, and then train it. Use that, the trained model using that hyperparameter, then evaluate it on the test set. Okay, so don't do cheating, especially in deep learning. Be careful. I myself, when I was a reviewer for papers, I caught this a lot. Sometimes I said you need to redo all of your experiments again because you have cheated. Okay. Justification of overfit. That's it. Okay. So we have this. Consider this estimation error. Now this axis, consider it as model complexity. You can see this as iteration as well. So your machine learning models, either they do their task either in one shot or they are iterative, right? For example, deep learning is iterative, right? Or some things that are in one shot. If they are iterative, you can consider this x-axis as iteration. Why? Because usually the more you train, the more complex you become, right? Therefore, it's either model complexity or iteration, doesn't matter. Then here I have the estimation error, my error. This error is empirical error. You can consider it as a training error. The training error usually goes down always. It might have some fluctuation. The overall pattern usually goes down always. Because you are training on that training data over and over. Of course, it gets better and better, right? However, initially, this is validation error. Also true error. Do you remember? I said in validation or test set, the empirical error is a good estimate of true error. So this is a test error or validation error. The validation error also comes down, but at some point it starts to increase. I think it makes sense. Why? Because here in this region, I'm performing very well on some specific data points, which are the training data points, but I'm losing generalization. I can't work well on the unseen data points. Then the error of the unseen data points goes up, right? When this happens, it is overfitting. In this region, both my training error and validation error are high, right? It's just initial iterations. So it's underfitting. We need the middle case scenario. That's a good fit, right? And as I said, overfit has low bias and high variance. So the more we go, the less the bias becomes, the higher the variance becomes. Here, we have high bias and low variance. This is a good fit, right? Now, let's justify mathematically. Why does this error go up? And this error, while this training error goes down, but this true error or validation error goes up. Can you tell me? Do you remember the formulas that we derived? I told you, bear with me. We'll see the beauty. Okay, these were the error. When instance is not in the training set, such as validation or test, this is the case. When the instance, data instance, is in the training set, this is the case, right? Then what happens? The more we go to this side, the more complex we become. The more this term becomes, the larger this term becomes. Then what happens? It says the difference of true error and validation error gets bigger and bigger. Gets bigger and bigger. However, so we know that from this, we know that you can see capital error, the true error, kind of as validation error, right? So let's replace this as validation error. And this as training error. Because of this, which is going up, this is increasing, right? This complexity term is increasing. This training error is decreasing, right? So you have two curves. What is the summation of these two curves? Because I have this plus this term, right? The first term plus the third term. The second term is a constant. Ignore it. The first term plus the third term. The first term is this. The complexity term, the third term is this. You have two curves. Add them. It becomes like this exactly, like this bowl. That's the reason. The validation error is going down and suddenly it goes up. You see that? You see the beauty. By the way, this beauty was discovered, at least as far as I know, the first time by Professor Rayleigh-Ritz at the University of Waterloo. How we can justify overfitting using Shor, Stein's unbiased risk estimate. Okay, so the credit is his. Okay. Professor Rayleigh-Ritz at the University of Waterloo. Yeah. Also watch his YouTube videos. He has Rayleigh-Ritz. He has good videos on YouTube. Okay, so yeah, I already explained these things. Now, this discussion of cheating in a nutshell. If we have only training and test, the training and test should not be contaminated. Otherwise, we have cheating. Cheating number one. If we have training, test, and validation sets, training and test should not have overlap. Otherwise, it's cheating one. Validation and test should not have overlap. Otherwise, it's cheating two. What if my training and validation have overlap? What happens? Assume I use my training data set for tuning my hyperparameters, because I use validation for training hyperparameters. Now assume I don't have validation. If I use test set for tuning hyperparameters, that's cheating. Cheating number two. Now, what if I use the training data for tuning hyperparameters? What happens? It's the other way around. When we do cheat, it's a benefit to us, right? When we use training for tuning hyperparameters, not only it's not cheating, but also it's a harm to us, right? Why? Because you're tuning your hyperparameters on training, so it gets overfitted more. You never find out whether you have overfitted or not. You're helping the model to get overfit, right? Regularization. Now, I want to minimize the true error, because the true error is important to me, right? Let's minimize the true error. This was a true error, right? Why am I using this formula for true error? Because I'm using training data. I want to train. Okay. This is a constant, get rid of it. The second term, right? The last term is complexity, right? What does this mean? It means that minimize the empirical error that you can see, minimize that the training error. However, also penalize the complexity. We are minimizing error plus complexity. So it means that we are minimizing both error and complexity. Minimizing complexity means to penalize the complexity. Let me consider this complexity as omega x. I can call it penalty or regularization term. Okay. So this is the regularization term, and the whole thing is a regularized optimization cost function. So this is the cost error, empirical error, but I regularize it by some regularization term with some weight alpha. Alpha is usually called the regularization parameter, and it's greater than 0 usually, right? It shouldn't be negative, otherwise minimization becomes maximization for that, right? Alpha tunes how much should I care about the penalty or the regularization term compared to the actual cost, right? The larger the alpha, the more I care about omega x compared to jx, right? Again, as you see, this regularization parameter is a hyperparameter, which can be tuned by validation. We use regularized cost a lot in machine learning, a lot. So we had this, I'm repeating that. Let J tilde of X be the regularized cost, while J of X is the actual cost, okay? By the way, this penalty term can be different functions. They usually use L2 norm or L1 norm or L21 norm, different norms for that. Again, recall preliminaries. Okay. The L1 and L21 norm are useful for having a sparsity. So whenever you have L1 norm, this should ring something in your mind that it's probably is used for sparsity. There is always in science, at least in machine learning, whenever you hear L1 norm, maybe it's related to sparsity. Why? We'll talk about it. Why do we use L1 norm? Why do we like sparsity? By the way, what do I mean by a sparse? When a jungle is sparse, what does it mean? When it is dense, it has a lot of trees. When it's sparse, it has several trees and the rest of it is. So sparse means that I have a lot of zeros in my, right, vector or matrices. Why do I like a sparsity? In machine learning, a lot of times we like a sparsity. And there are at least two reasons. The first reason is betting on a sparsity principle. It was proposed by Hastie and Tibshirani at Stanford University. What did they say? They said, give me an algorithm, but in two versions. One version, dense version of one algorithm, the same algorithm with a sparse version. And make me blindfold. Okay, blindfold. Give some data to them, and they will give you some accuracy or some performance, right? Without even looking at the results, I bet that the sparse model worked better. This is called betting on a sparsity principle. Okay. Use a procedure that does well in a sparse problem, since no procedure does well in dense problems. This is what they have said. Okay. Another reason is in logic and philosophy. Have you heard of Occam's razor? What is Occam's razor? Occam was an ancient logician and mathematician. He said, when something in the world has several explanations, the simpler explanation is the better one. This is Occam's razor. I give you an example. I need to give you exaggerated example for you to understand. Assume I'm hungry. There are several explanations for that. Either I haven't eaten for several hours. This is one explanation. The second explanation is that an invisible alien came and tricked me and made me hungry suddenly. Both explanations explain why I'm hungry. Both. But which one is valid? Which one should I say that is the correct explanation? Of course, the first one is the simplest. There's no alien, right? Okay, so here also according to Occam's razor, when I can get good result with a sparse data or sparsity, why do I make it dense? Right? Okay. So now we are minimizing the J tilde, which is the true error, right? The regularized error, and not the empirical error or J. Again, this is because regularization helps avoid overfitting. Do you agree? Why? Can you understand it? I want to understand the depth of this. Here we are minimizing the true error, and the true error has the overfitting in it. So I'm also minimizing the overfit. Therefore, regularization is useful for us to not have overfitting, to avoid overfitting. L2 regularization. Now, rather than that omega x, I use squared L2 norm. Why don't I use only L2 norm? Why don't I use only L2 norm of x? What was a squared L2 norm of x? Recall preliminaries. It's quadratic, right? X transpose x. It's like a bowl. What about normal L2 norm of x? It's not even convex. Not even convex. Why do I add a non-convex cos to make my cos complicated? So I add squared L2 norm. Why do I put division by 2 here? It's optional. Because I know that I eventually want to take derivative. It's optimization. And I know that the derivative of squared L2 norm is 2x. I want to get rid of that 2 by dividing by 2. Right? This L2 norm regularization is also referred to as ridge regression or Tikhonov regularization. Of course, Tikhonov must be a Russian mathematician. Russia has a lot of good mathematicians. Suppose x star is a minimizer of the function j, right? This empirical error. Suppose x star is there. Derivative of j of x star is 0. Why? According to the first order optimality condition, high school, right? Now consider the Taylor series expansion of j up to the second derivative at x star. Okay. By the way, try to understand this. These proofs don't come to exam, right? Just try to understand. Okay. So I have this j hat, which is the Taylor series expansion, up to the second term, second derivative. This h is the Hessian, right? This interestingly goes away. It's 0. Why? According to equation 25, first order optimality condition, because I'm considering the Taylor series expansion at x star. So it simplifies to this. So I had these, I'm repeating them. Now, put this in place of j, this Taylor series expansion. Then I will have this plus the regularization term. What should we do? I'm minimizing this. Take derivative, set it to 0, right? So I take derivative of this j tilde, set it to 0. I'm setting it to 0. What is the derivative of this term, jx star? Note that it's not jx, it's jx star. I have put x star in the function. It gives me some scalar. It's constant, it goes away. Its derivative is 0. It's not jx, it's jx star. What is its derivative? It's a quadratic form. So it becomes 2h x minus x star. And that 2 and 1/2 cancel each other. So we'll have h x minus x star. Why have I put x dagger here? Dagger, because I want to say that this is the solution. You can consider it as x, doesn't matter. Okay. And the last term, its derivative is also alpha over 2 times 2x the 2's cancel each other. We'll have alpha x. Set it to 0, rearrange the terms, and factor out the x or x dagger. Then left multiply the sides by the inverse of this. So get the x. This is the solution, right? I think hopefully we can have enough time. I don't know. Then I think we don't have enough time to go through this unless you want to stay longer. But I think you're tired. So let's stop here. Just to let you know what we're going to do. We will see that we will solve this. We'll go further and further. And we will see what impact this regularization term has. Okay. How it shrinks some directions of the solutions and does not impact other directions. This is one case. And then we will talk about what L1 norm regularization, and then we'll compare L2 norm and L1 norm regularization. And we'll see that why is L1 norm making it sparse? And why is L2 norm not making it sparse, but also shrinking? We will talk about it. And afterwards, we'll start regression and the classification algorithms. Okay, thank you.